Okay, so welcome everyone to another session of EPICentre seminars and discussions, the online edition. Today, as you can see, we're honored to have Jonas Cels to talk about Tsunami Variable Depth Pushover Toolkit for design and assessment of structures. As always, I'll give a short introduction to Jonas, and then Jonas will share his screen and talk about his project. So Jonas Cels is a research assistant at UCL and EPICentre, investigating the tsunami vulnerability and resilience of critical infrastructure, developing the methods and tools necessary for practical application. Jonas joined us at UCL as an MSc student in earthquake engineering with disaster management. Before that, he was a practicing architect on large-scale infrastructure and residential projects, including Crossrail. He's currently pursuing his PhD degree at UCL, investigating the system-wide tsunami vulnerability and resilience of school networks in Sri Lanka and Maldives. Jonas, we're honored to have you here. Whenever you're ready, please share your screen.
Thanks very much, Arash, for the introduction and for everyone to join me on this talk. I'll just share my screen. Okay. Can everyone see that? And can you...
Yes.
Okay,
perfect.
Great. So I'll be, as Arash mentioned, talking about a Tsunami Variable Depth Pushover Toolkit, which was developed as part of my PhD research and is in application for schools in Sri Lanka, and also will be for the school network in the Maldives. So I'll be talking about what variable depth pushover is, but the starting point of the talk and of a lot of the methods, at least at EPICentre, developed to understand and assess structures in response to tsunami loading starts with the 2004 Indian tsunami. I'll then be talking about the motivation behind the toolkit and why I've developed it. Then I'll give an overview of how structural fragility is assessed under tsunami loads, continued by the Toolkit Framework. And if there's time at the end, I'll go over some of the further applications of the toolkit. So the December 26th, or the Boxing Day tsunami in 2004, occurred when an earthquake in the just southern Sumatra, along the northern Sumatra Andaman subduction zone, an earthquake of moment magnitude 9.1 to 9.3 erupted, and the rupture was 1,200 kilometers in length. So to give you a sense of scale, the UK, when I measured it, was in height 900 kilometers. So the rupture is even greater than the entire height of the United Kingdom. And essentially the Burma plate slipped above the Indian tectonic plate at an average height of about 10 and 15 meters in certain regions. And that produced a wave which propagated across the Indian Ocean, as you can see here, and resulted in catastrophic losses. So the tsunami caused 226,000 casualties across 13 countries. And in Sri Lanka, it had very high impact on the school network. So it damaged and destroyed 182 schools across the coast. So the impact was heaviest in the eastern district here in the Ampara and the Batticaloa regions, as well as in the southern region here in the Galle district. So in total, the number of schools that were affected was 5% of the entire school building stock. So schools played a critical role in the recovery of communities. One, they served to accommodate students that had lost their school through student transfers, but also many schools acted as emergency shelters for hundreds of thousands of people that were made homeless in Sri Lanka. To just give you a sense of the recovery, it took around 2 years for most schools to be reconstructed and rehabilitated. However, to show the resilience of a school network doesn't only depend on the physical assets of the school network, but it also depends largely on the functionality of surrounding schools. And so students in the most heavily affected regions were able to return within 2 weeks, between 2 weeks and 2 months after being struck by the tsunami. Okay, so that brings me to the motivation of the toolkit. So currently there are 430 schools which are directly exposed to a tsunami hazard, and that equates to about 193,000 pupils across these schools. And that is about a 4% increase since 2004 figures. The toolkit, the aim of the toolkit is to facilitate a tsunami loss assessment countrywide, which thus requires a systematic approach to assess school buildings against tsunami impact. And the aim is also to combine and advance the latest tsunami analysis methods into a single systematic framework and tool. So tsunami structural analysis is a fairly recent discipline, which, as I mentioned, started really at EPICentre and with the 2004 tsunami. So, and there's no structural analysis software which is available for the fragility assessment and the design of structures against tsunami loads. Lastly, the objective was to make tsunami analysis accessible to engineers in Sri Lanka and beyond, without the need of prior open seas knowledge. And I'll be talking more about that in just a second. And the image on the bottom left shows an evacuation sign that we found at one of the schools when we surveyed them. And so a lot of schools have designated 2 or 3 story school buildings as their vertical evacuation structure. So that raises a very important question as to whether these schools are safe or not to serve as vertical evacuation structures. So before we get started, there's just some, like to kind of familiarize you with some of the characteristics of tsunami forces and their interaction with structures. So the tsunami wave, or the tsunami period of the 2004 tsunami, was approximately 40 minutes long. So it has a very long period. So in relation to structural periods, which ranges, between 1 or 2 seconds, we can use a static approach of analysis because the difference in structural period versus the tsunami period is so large. And I promise this is the only equation that I'll be showing today. And so this is an equation showing how the forces are estimated when they interact with obstructions or obstacles in the tsunami flow, i.e. Buildings. So what I want to draw your attention on is The B underneath the FT is the total force acting on the obstacle. So the B stands for the width, so the width of that obstacle, or the tributary width. Then also there in the equation is the H, which is the height of the tsunami inundation. And the third variable I want to draw your eye to is U, which is the tsunami flow, the velocity of the tsunami flow. So what this tells you is essentially that the forces exerted on a structure are a function of the surface area of the obstacle blocking the tsunami flow and the wave velocity. Okay, so what is a variable depth pushover? So it's similar to a seismic pushover in that it's a static procedure, but in this case, and it consists of two phases. So the first phase is a force-controlled phase, and essentially the inundation is gradually increased up to a maximum height, which I've shown here, and the tsunami forces are calculated and applied to a series of points along the structural members or along the columns. The forces are increased in relation with respect to the increase in inundation height. And then, as with a seismic pushover, we measure the top displacement and versus with the base shear, or the force resisting the lateral tsunami loads. And recent developments have kind of improved this method to account for buoyancy forces. So as the inundation rises above the first level and the second level, because of the downstand beams, which create air pockets underneath the structure, that produces a lot of vertical upward pressure on the structure, in addition to the lateral drag forces. Okay, one of the disadvantages of a force-controlled method is that it doesn't capture the degrading branch of the capacity curve of the structure. So to get around this, Marco Beguera has kind of expanded on the method and added a second phase of the procedure, in which once the peak capacity of the structure is reached, or the inundation height reaches a predefined set maximum height, the analysis switches to a response-controlled phase, and this is akin to a seismic pushover, where the structure is displaced and then the forces are back calculated. And so at the constant depth, at this phase, the inundation height is held constant, and then the drag forces are increased in proportion, as shown here. So the way the Toolkit framework works, it uses OpenSeas to conduct the analysis. So there is a structural modeling component, a tsunami modeling component, which essentially calculates all the input forces, the lateral and the vertical buoyancy forces. Then there's a execution module, which runs the analysis in OpenSeas. And then there's a post-processing module. So the structural model is made of there's a user interface component which uses Excel. So the user can model their structure in Excel. Then there's MATLAB script, which extracts everything from this Excel model and builds automatically an OpenSea structural model without the need of the user to use OpenSeas at all. Okay, and then there's the Tsunami force model. So this component calculates all the forces which are input into the structure for analysis. So again, it's a Excel user interface where the user can define the characteristics of a tsunami based on hazard data as well as site conditions. And the MATLAB tsunami force calculator will then take the structural model that was just built in the structural model builder and calculate the forces based on the structural interaction with the tsunami flow regime. And so here you see that each of these are the forces acting on each of the columns along the structure. And I'll be now talking about how these forces are calculated. So to illustrate kind of what's going on in the background, we are going to inundate a 3-story school, and this is one in Sri Lanka, and it's a typology commonly found across Sri Lanka. So it has 2 rows of columns, a central staircase, as you can see here, and then 2 classrooms on each side. So let's raise the inundation up to 2 meters. So the drag forces here, depicted in red, are acting on all the columns in the front face, and the tsunami flow is acting kind of against the long edge of the building. We can assume that these walls here, because they're not confined with columns, have very low out-of-plane capacity. Oops. So the forces, the drag forces, will also act on the back face and be exerted on the columns here. So the schematic here at the top shows that the forces acting on the column, because they have the surface area acting on the column is much narrower or much smaller than the back face columns, which have the infills. You can expect that the forces acting on the back face columns will be much greater than those acting on the front face columns. So the way that forces are calculated, drag forces are calculated and redistributed is depicted here. So we can imagine that we've developed a new method for using yield line theory, so that we can expect that some of the forces acting on the infills will be redistributed either down to the foundations or to the beam supporting the infill below it. The 2 triangles here will those forces will be redistributed to the columns on either side, and then the top trapezoid here, those forces will be redistributed to the top beam as shown here. And so the way the calculation works is the height of the infill panel is divided up into, discretized into a number of strips, and that area gives you the acting on that surface gives you the pressure, and then that pressure is summed up and applied along these application points, which are the white rectangles along the height of the column. So as you saw from the image from of the school, the facade or the external envelope of the building is variable. So the model allows you to create essentially different panel models, which allows you to model the infill properties, as well as the beams and the columns, which will not fail out of plane. So here's an example here. This central one shows the ground floor column. So we'll expect a constant width along the height of the column. And then once the inundation reaches the beam, the tributary width will increase to, well, in this case, 3.1 meters. And then on the first floor, you have the parapet, which is made out of masonry infill on either side of the column. Then you have an opening, and at the top, you have the beam. So here you can see how, because the surface area increases once we increase the inundation up to 3.5 meters, you can see the effect of the tsunami forces acting on the structure. So there's one important point to raise here, and that's the difference between hydrodynamic and hydrostatic forces. So the toolkit allows you to make the assumption of whether the school is impermeable or whether your structure is impermeable or permeable. If it's, and so the forces are really made up of two components. One is the hydrostatic force, which you would get in case of just a static flood condition. And then you have the hydrodynamic force, which is a uniform distribution as shown here. Because this school, we have, because there is the staircase in the middle, and we can assume that the water inside the structure would rise along with the flow on the exterior of the building. These two static components of the force essentially will cancel out because there's static hydrostatic forces acting on both sides of the columns, and thus they cancel out. And at 3.5 inundation, we also start to observe the upward buoyancy forces. As I mentioned earlier, they act underneath the floor slab. And so the user is able to define the out of plane capacity of these slabs. Once, let's say, the slab fails and water essentially punches through the floor slab, then those upward buoyancy forces will be released. And this image here is it's an image of a car park in New Orleans just after the Hurricane Katrina flood, and it's just to demonstrate the magnitude of buoyancy forces. So where the red dotted line is shown is where the floor slab used to be. Essentially, it was pre-tensioned beams which were uplifted because they had huge kind of coffers of air underneath them because of these very deep beams, and the floor slab essentially was lifted up, and then once the water received, it dropped back down to the level you see in this photo. So let's raise the inundation now up to 6 meters, and here this is to show now the behavior of the infills and how that really affects the forces exerted on the structure. So in plane, as with the seismic, the in-plane masonry infills will start to form compressive struts, which is represented in the red line, diagonal line here. And out of plane, we can assume at some point the out of plane capacity of the infills will will be exceeded and the infill will fail. And so then you have a reduction in the drag forces because the surface area decreases all of a sudden. And also if you have a, as I was showing, the parapet was protecting the rear face of the structure from drag forces. Once that fails, we can assume that the tsunami flow extends to the back face of the structure and exerts forces as shown on the top right diagram. And that raises kind of a question of high uncertainty. In the aftermath of the 2004 tsunami, many of the schools demonstrated blowout infills, but there were also components that were that remained stuck on, and essentially there's no empirical tests to give us any guidance on how great of a percentage of the infill will remain stuck on. So the approach that the toolkit takes is, again, using yield line theory. We're assuming that the bottom trapezoid will completely wash away, and then a portion of the infill will remain stuck on. That can be treated by a random factor. Okay, so this is kind of how representation of it on the right hand side. And then those forces will, that surface area will continue to attract forces on the column and redistribute them directly to the column. So these are essentially the time series for the columns here on the right, and then the beams, the vertical loads of the beams on the right hand side. And as you see, there's for the lateral columns, at some stages there are sharp reductions, which are kind of shown by these horizontal lines, and that's when infills fail. And then here you can see once the inundation reaches 3 meters, which is the first floor level, there's a dramatic reduction in the distributed loads on the beams. And so the effect of that on the columns is a reduction in the actual axial forces and consequently a reduction in the shear capacity of the columns as well. And so let's hope this works. This is an image showing the how the lateral time, the lateral drag forces acting on the column. So you can see initially here there's, well, kind of step decreases in the drag forces, and that occurs when the infills fail. Okay, and then on the right hand side is the net reaction with respect to tsunami inundation of the columns. Sorry, of the base nodes. Okay, so further applications. So there is a module that allows you to assess structures and compute the loads using the ASCE 716 formulations. And you can conduct systemic as well as component level checks. And there's a link to the paper that discusses that in further detail. The toolkit also, because it's created it's modular, you can build your 3D structure, and then one of the aspirations is to build plugins in order to be able to conduct seismic analysis. We'll also expand it to be able to model steel frames. and lastly, what I'm currently developing is a fragility function generator. And that is it from me. Thank you for your attention, and I'd be happy to take any questions.
Perfect. Well done. Very interesting, as always. And I can see it's a massive collaboration of some of our colleagues in EPICentre throughout the years. It's coming to a, let's say, not an end, but to a point that is like getting applied to reality. As always, the floor is open. Whoever has any questions, please raise your hand or feel free to unmute yourself. I have some questions. Let's start with the further applications. Have you guys thought about non-structural elements, specifically in schools? That causes so much problem. Just imagine a school classroom with thousands of chairs and tables and blackboards and stuff. The tsunami gathers all of these, and that will be an exerted force on the infills or wherever the tsunami wave is taking all of these. Have you guys considered, or has it reached to that point?
Okay, so I'll answer in two parts. So I think maybe, are you referring to kind of debris impacts and things like this?
Yes, the debris considering schools. Let's not make it sophisticated that suddenly a car comes into your house. So yes,
okay,
let's concentrate on schools.
Yeah, so the procedure developed with Beguera, Marco Beguera, excuse me, that looks at a way of assessing, making sure essentially that if an individual column is impacted by debris, and the ASEE has formulations in order to try and estimate what an debris impact might look like. You can assess just that component or that kind of bay or column to make sure that then the total structural response, that the structure as a whole remains intact, given kind of inducing greater forces on a specific column or bay. We are looking at non-structural damage. We've obtained an empirical damage survey, very detailed, following of schools in Sri Lanka. We're assessing it currently, and that has tabulations essentially of how many desks, chairs, and other non-structural, or computers, other non-structural elements of the school that were lost. So our approach will be to answer that question empirically and develop empirical fragility functions based on that data.
Okay, fair enough. Makfira, I just saw that you raised your hand.
Yes. Thank you, Arash. Thank you, Jonas, for your presentation. Yeah, I'm wondering that you define the forces as hydrostatic or the angular distribution of forces. But is there any correlation, or how significant the density of the water, which sometimes like bring the sediment or part of a collapsed building? So is it takes into account the mechanism of hydrostatic for applying the forces in the building?
Yeah, thank you, Maggie Fira, if I said your name correctly. So the fluid density is considered here. So I think it varies for sea. So you would put in the fluid density of seawater, and that does affect the forces exerted on the structure. And I'm not sure if that answers your question or not.
Okay, yeah. But maybe like how to define, the fluid density is maybe not uniform. So many materials that like bringing by the water. How you like to measure the density itself? I mean, it's not uniform. I mean.
Yeah. So so debris would be. So the ASCE has formulations to estimate debris impacts, and what, let's say, so often there would be, let's say there's palm trees or let's say, or a boat or something that would get dammed against the structure. That would increase the surface area against which the water flow acts, and then that would get redistributed to the columns. So the way we would model that using this framework would be to set a, let's say, define a greater tributary width to those columns, if that makes sense. So we would make that width, let's say that the damming is, I don't know, 70% of the bay area. We would create kind of similar to an infill, but we would create a surface area against which then the loads are calculated.
Yeah. Okay. Thank you, Jonas.
Okay. Alvaro, it's very good to have you here. If you have the question, please.
Hi, Alvaro.
Yeah. Hi, Jonas. Hi, Arash. Nice to see you guys, and very good presentation, Jonas. Very interesting. What I was wondering is, you mentioned that the tsunami wave has a very long period, and you're analyzing it in a static load scenario.
Yeah.
So I was wondering if you thought that this would be also applicable to flash floods or conventional flooding. And you mentioned the example of Hurricane Katrina, but maybe you would have to tweak it or not. Just wondering what your thoughts are there.
I think we could, I mean, for flash, so with tsunami wave, so let's say with the flash floods or coastal, kind of coastal waves, you would get an initial bore force, is what it's called, is kind of an initial impact. When the wave first impacts the structure, you get an impulsive force, as shown here. In tsunami, because the rise in inundation is so gradual, that bore force isn't really shown to be dominant. So it's not something we consider directly in the formulations. It's much more the drag forces. So, but yes, absolutely, we could modify essentially we would replace this tsunami model, which calculates the loads, replace the equations to include those bore forces, and where you then define the flash flood parameters, and then it would work with everything else.
Good to know. Thank you.
Thanks for joining.
Following Alvaro's question, what are you going to present your fragility curves based on? What is the intensity measure in that case? Have you guys decided on that? Water height, water velocity, something new?
Yeah, so that's still an unknown at this stage. So we're also looking at moment flux. So the tricky thing is, okay, you have the intensity measure of the tsunami, but because the actual forces exerted on the structure are a function of the structure itself, of the surface areas and the infills and so forth. It's dependent on the tsunami scenario as well as the structure.
Yeah, it gets sophisticated. Yes, for the performance points as well. Like, how are you measuring the response can be displacement, but yes, how you're going to represent the tsunami. Yeah, good luck.
So yeah, we're thinking maybe as if somehow proportional to the total envelope width, for example, and then
Okay. Another question is like, usually in flooding, we consider the loading as triangular. Flash flooding, okay, can be reversed as well. Are you guys considering the whole thing rectangular, or is it variable? Because in some images, I can see variation. In some images is represented with a rectangle. Is it?
So it depends on whether your structure is impermeable or not. These schools, because you have the staircases, and so the water would kind of come up through the staircase, and then you'd have a stagnant pool occurring on that floor level, roughly in height with the water outside. So those hydrostatic element components would cancel out. And so then we just assume a rectangular distribution for the drag forces. But
okay.
the toolkit does allow you to phase it so that you can assume that it's impermeable. So I think many of the studies that were conducted before assumed impermeable structures. So it assumed, and therefore it's you'll see, if you go back to those papers, you'll see triangular loads.
Okay. One other thing is, again, following this concept, okay, makes sense. Yes, this and that, they omit each other, so you're just left with the dynamic load. Generally, like in wind, for example, we have the push and pull, the push and suck on one side. When the inundation of tsunami ends and the water goes back, do you guys worry about that, or like have you considered that, or like we shouldn't worry about it?
No, absolutely. So, okay, so if you think of a tsunami wave as a sine wave, so the inundation rises and rises, and about 2/3 of the maximum amplitude or the maximum height of the wave is when you reach the maximum flow velocity. And then as it continues to increase, the velocity will start to decrease until it reaches the top and the velocity is 0, and then the direction will reverse. But those forces occurring in the reverse direction are, just as large probably as those in the initial run up. So if you, after the Tohoku tsunami in Japan, you'll see a lot of the buildings were actually kind of drawn out to sea, and so that shows you the significant loads in the tsunami drawdown as well. That is also an aspiration that we will look into next. But the main kind of factor there is scouring, and I believe I showed you a photo here. So the schools in Sri Lanka that are built along the coast mostly sit on sandy soils. And so as the inundation, as the tsunami flows past the structure, it scours, or essentially digs out a hole around the edges of the structure. And so if that process continues long enough, and you see it very clearly here, it completely undermines the vertical support of the structure. It undermines its foundation. So what we've seen a lot is that then this structure essentially collapses into the scouring hole.
Okay, so that's an additional issue that you have.
Yeah.
Yeah, and yes, regarding the previous thingy, that's the inundation causes the same value. Like the problem is like when the tsunami hits and it causes some damage, then the progressive damage, your structure isn't the same thing. When it's coming back, your structure is weaker. So yes, definitely the damage will be higher as well. Yeah, good luck in calculating that as well. Anyone else has any other question? No questions. Okay. I'm just looking at my notes whether I have any other question. Yes. Recently, Seismostruct, the 2022 version, has introduced a Tsunami loading, which is based on ASCII 7 2016 version, as well as the Foster. Just in a very short way, is there any major differences? What are the major differences between the ASCII and the Foster?
Okay, so
just for general knowledge.
I've not actually used the Seismostruct version, but there you can only apply loads as point loads at each story level, so at the ends of columns. What past studies have shown is that because loads are applied along the height of the column, you get a buildup of shear forces, and so you wouldn't get that same type of behavior in Seismostruct. I think the Seismostruct would be able to model, let's say, a bare frame structure, but it wouldn't be able to model the variable surface areas and the properties of infills. So you don't. That is kind of one of the major improvements in the method is the variable nature of let's say the structural response in terms of tributary surface area.
Okay.
And I also believe it doesn't have buoyancy forces, which are very significant. So in this case, they reduce the axial loads on the columns by about a third for each level that the inundation rises up to.
Okay, the question was mainly what is the difference between ASCII and Foster, but you explained what is the difference between your method and Seismostruct. Thank you very much. But in few sentences before we finish the session, any major difference between ASCII and Foster's methods?
It's mostly on the way the short answer is two different equations of estimating the drag forces.
Okay, there are extremely different spectrums, or like
no, they're so the Foster's way uses the Froude number, where the ASCII way you input the flow velocity. So here in the Foster's method, we assume a constant Froude number, whereas the other method is variable. So it's different input parameters, in short.
Okay, perfect. Thank you very much again. Any last questions before we close it down? Okay, so I'll just share my screen for a second. So yeah, so today we had a Tsunami Variable Depth Pushover Toolkit for design and assessment of structures. Thank you very much to our speaker, Jonas Cels. Very interesting, and good luck in developing this, and hopefully you'll come up with a proper package all the way to losses. Next week we won't have any seminar, but on 23rd of March, in 2 weeks, Dr. Tayo Opabola will be talking about seismic assessment and nonlinear modeling of as-built and rehabilitation concrete structures with bond deficiencies. Tayo will probably show what happens in the experimental lab, let's say, explores, as well as how we implement that in nonlinear softwares like OpenSys or SAP 2000. So with that, thank you very much again for joining us. As always, all of the recordings will be available in our YouTube channel as well as EPICentre website. So good luck, and we'll see you in 2 weeks. Thank you for attending. Bye.
Thanks, Arash.
Thank you.
Thank you, Jonas Cels. Bye.
Bye.